Okay, so we learned in chapter 8, we are learning about these infinite series, and we are learning about different tests that help us determine if an infinite series converges or diverges. Of course, an infinite series is when you add an infinite number of terms of a sequence. And does that series converge? Does it converge to a finite number? So to determine if the sum converges, you have a variety of tests. For instance, the limit comparison test, the regular comparison test, the alternating series test, the ratio tests. All these tests are designed for different types of series. Um, and usually the ratio test is reserved for the most complicated series. Uh, so this is nice that we're learning this, and and we do recognize that even if the terms of a series approach zero, that does not mean the series will necessarily converge. And that's why we need to be cautious and why we need to use these tests. Because the tests, there's an intuitive feel using the tests, and I think it helps make things clear using the different tests. So like for your exam next, which will get posted next Tuesday, for exam 4, if the power series converges or diverges, you might, there might be a multiple choice where you answer, converge, diverge, but then it is possible I'll want work to back that up, right? So you want to be applying these tests and thinking about them. So it's nice we're understanding about infinite series, but remember, we ultimately want to study functions too. Can we relate a series to a function? And the answer is yes to that. The answer is yes. A power series is a series of this form. So you notice there's a variable x now in the series, a variable x in the series. All right? And if we were to write the sum as n equals 0 to infinity of cn x to the nth power and write out the terms, we'd have c sub 0 plus c sub 1 times x plus c times 2 times x squared plus c3 x cubed. Okay, and the cn's are called the coefficients of the series. Okay, now power series may converge for some values of x and diverge for other values of x. And you had a little bit of, you saw a few power series back in section 8.2. How many remember you had a couple problems where it said find the values of x for which the series converges? And it turned out they were geometric series, and you had to write an interval over which the series converged. How many recall those? You had just a few problems back in section 8.2. Does anybody remember those? Well, you've seen it a little bit, but of course now we're going in, full force in section 8.5. So, all right, the sum, and this is very important here, the sum of a series, and maybe I'll have it in yellow. Maybe I'll have it in yellow. The sum of a series is a function. Okay, the sum of a power series is a function whose domain is the set of all x for which the series converges. Okay, so, I mean, ultimately what we're going to do is we're going to be taking functions and representing them as these power series. Okay, so we can take, so like we want to take functions eventually and write them as power series. And the power series here that I've highlighted, where n equals 0 to infinity x to the nth power, that's going to be, that's 1 plus x squared plus all the way, you keep going. That's a geometric series. with a common ratio of x, right? This series here, I'll highlight it in pink, this series here is a geometric series with a common ratio of x, right? Because 1 times x is x times x is x squared, and so forth. Well, this series, this power series, will converge when x is between -1 and 1, because that means the absolute value, that's the same thing as saying the absolute value of the common ratio x is less than 1. And that power series diverges when the absolute value of the common ratio x is greater than or equal to 1. Okay, so this is this is what we're going to be working with. This is what we're going to be working with here. And series, these power series come up a lot. There's a series called a trigonometric series that you'll see in some applications in some of your other courses. And where the series, for what values of x the series converges, and for what value of x the series diverges is very important. So we are going to do a couple examples, like together, but I want to look at a few of the, well, I want to look at one of the book examples before we go to my examples. But I'll mention something else too. This series here in Formula 2, okay, this series here is called a power series in x minus a, or a power series centered at a, or a power series about a. Okay, and because you see, you have in the right-hand side, you have like the terms x minus a squared. Then you'll have x minus a cubed and so forth. So this kind of power series is something you're going to see a little bit later in chapter 8. All right, so it's sort of like giving you an idea of what's coming up here. All right, so let's just look at a very simple example. Example 1. For what values of x is this power series, n equals 0 to infinity, of n factorial x to the nth power convergent? Okay, for what values is that power series convergent? Okay, well, let me ask you, looking at that power series, the n factorial portion, the coefficient in front of x to the nth power, what happens to n factorial as n increases? So when n is 0, okay, we have 0 factorial. 0 factorial is 1. And then n is 1. 1 factorial is 1. And then n is 2. 2 factorial is 2 times 1. Okay, n equals 3. That's the next term. Well, that's the next value of n. You get 3 factorial, the coefficient 3 factorial. That's 3 times 2 times 1. What happens to the coefficient n factorial as n gets larger? Does that coefficient get smaller or larger with n? The n factorial coefficient in front of x to the nth power in this example 1. That's right, it gets larger. That's right, Tina, it does. N factorial grows with n. So the terms of this series, the fact that the coefficient gets bigger and bigger and bigger, might lead you to believe that this series, it's not gonna converge for really any value of x. And except x equals 0, because if x equals 0, what's the series equal to when x equals 0? What's the series equal to? If you were to substitute x equals 0 in for x, what would all the terms of the series equal? That's right. Good, Tina. Good, Mohammed. 0. And you would just have 0. So the series would converge when x equals 0. But if x is anything else, the series should diverge because the coefficients are getting larger, and you know, the n factorial coefficients are getting larger. And to sort of confirm this, you see, we don't have to just rush and use, we're going to use the ratio test. You're going to use the ratio test for all the problems in section 8.5. But we don't have to just, you know, we can look at the series a little bit and try to use our intuition. But now we use the ratio test to confirm our result. So the ratio test is the ratio of the n plus first term of the series divided by the nth term of the series. And the nth term of the series, in the denominator there, is n factorial times x to the nth power. In the numerator, to get the n plus first term, you replace n by n plus 1. And so the limit as n goes to infinity of the ratio will reduce to the limit as n goes to infinity of n plus 1 times the absolute value of x. You know, n plus 1 factorial divided by n factorial is equal to n plus 1. Okay, does anybody want me to show the part where n plus 1 factorial divided by n factorial equals n plus 1? Does anybody want me to go to the whiteboard and show them that? Or are you, hold on. Okay, all right, I'll do that. I'll come back to this example. Let me share the whiteboard here. Okay, so let's just take a little simple example. 3 factorial over 2 factorial. 3 factorial, of course, is 3 times 2 times 1. And 2 factorial is 2 times 1. You get 3, right? Let me know if you have any questions. If you had 4 factorial over 3 factorial, 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. You're going to get 4. So far, so good. Are there any questions so far? All right. Well, now let's look at the n plus 1 factorial. One moment here. N plus 1 factorial over n factorial. Well, n plus 1 factorial, of course, is n plus 1 times n minus 1. all the way down till we get to 3 times 2 times 1. The denominator, I'm going to let be n factorial. Okay? But what is n times n minus 1 multiplied, with all the factors times 3 times 2 times 1? What is that equal to? N times n minus 1 dot 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 times 3 times 2 times 1. What would that equal? N factorial. That's right, Tina. So this is going to equal then what? What happens here to the n factorials? Right, simplify out, and you're left with n plus 1. Okay, and incidentally, for these, like these two examples here, when we had 3 factorial over 2 factorial, 3 factorial can just be written as 3 times 2 factorial, right? Two factorials simplify and you get 3. 4 factorial over 3 factorial. Four factorial you can write as 4 times 3 factorial. Right? Because what is 3 times 2 times 1? That's 3 factorial. Right? So do you, and then you get 4. Do you get, are you, who's a little more comfortable now that that it makes sense that n plus 1 factorial over n factorial would equal n plus 1? Okay, Tina's good. All right. All right. Michael and Mohammed, excellent, excellent, excellent. Well, so that being said, let's go back to the if there are no questions on that, we'll go back to that example 1 from section 8.5. Are there any questions at all? Okay. Let me go back to that example then. Oh, right. Hold on. I want the book, right? One moment. Okay. So now we're back to this example, and now we're okay with the limit of the absolute value of the ratio as n goes to infinity. That'll equal the limit as n goes to infinity of n plus 1 times the absolute value of x. Okay, because x to the n plus first divided by x to the n is x. But notice we can't remove the absolute value from x because x could be a negative number, right? So we have to have the absolute value stay on the x in this case. But x is just some value. X is some, I mean, it's a variable, but the variable will take on different values. And as n plus, for any value x is, since n plus 1 goes to infinity, the limit of the ratio equals infinity. And infinity is greater than 1. So by the ratio test, the series diverges when x is not equal to 0. The given series converges only when x equals 0. So this is an example of a power series that converges at just one point, x equals 0, for one x value. Okay, are there any questions on that? Okay, well then let us go ahead and look at an example here. Okay, and let me give you a moment to copy this example down. Okay, so here we want to find the radius of convergence and interval of convergence for this power series. Okay. Now, an interval of convergence simply means the values of x. An interval of convergence simply means the values of x for which this power series converges. The radius of convergence is if you take the length of your interval and cut that in half, and that gets you your radius of convergence. All right, so are there any questions so far? All right, well then let's go ahead and move forward here. By the way, what kind of series is this with the -1 to the nth power there as part of the coefficient? Good, it's an alternating series. So the coefficient is -1 to the nth power times n squared over 2 to the nth power. That's the coefficient of your x to the nth power. But all right, so what I did here was I wrote out just some terms of the series for you. Okay, I wrote out some terms of the series. Okay. So I let, I let n equals 1. I let n equals 2. So when n equals 1, I got this term here. When n equals 2, I got this term. The power series gave me that term. When n equals 3, the third term of the power series is this term here. And if I simplify things a little bit, the power series is going to equal -x over 2 plus x squared minus 9/8 x cubed, and so forth. It keeps going. I just thought it would be helpful just to write out some terms of the series, just so that you just have kind of an intuitive feel. So it's a polynomial, but it's like a polynomial with infinite degree, right? And we want to know, for what values of x does this power series converge? Whoops, hold on. Let me bring it back. Right. Okay. So, well, all right. How are we gonna determine the values of x for which this power series converges? How are we going to determine our interval of convergence? What test do we have to use? The ratio test. That's right, Rodrigo. Very good. And so we'll do that. So the ratio test, I'm going to let a sub n be the nth term of the power series. And I'm going to look at the ratio of the n plus first term to the nth term. Well, the absolute value of that. And then we get this is the first step. So let me give you a moment just to, copy that down. Let me know if you have any questions. Okay, so, all right, now what we have here, of course, is the absolute value of the ratio of two fractions. So we know when we have a fraction divided by a fraction, we take the first fraction, the numerator fraction, and multiply by the reciprocal of the fraction in the denominator. And that's what I've done here. And then what I like to do is I like to group things together. Okay, I like to group things together, like similar terms together. So -1 to the n plus first power, I put it over -1 to the nth power. And n plus 1 squared, I put that over n squared. 2 to the nth power, I put that over 2 to the n plus first power. And x to the nth x to the n plus first power, I put that over x to the nth power. It just helps me organize this. There's a lot going on, a lot of terms, and I like to group things together so that I can easily reduce. Okay, and when I reduce, when I simplify, I get the absolute value of -1 to the first power times n plus 1 over n, the quantity n plus 1 over n squared, times 1 over 2 to the first times x to the first. Are there any questions up to here? All right. Are we ready to go to the, so we have to take the limit of this expression. All right, let's proceed to the next page then. Well, let me ask you this. What happens to the -1 to the first power? -1 to the first power is -1. But does that go away? The -1 there? Is that going to go away? It is going to, well, I don't want to say it goes away, but it's going to become a positive one, right? And why is that? Why is that, Michael or Rodrigo? Good, absolute value, right? Good, everybody. So, okay. Well, then this is what we have right here. The limit of the absolute value of the ratio of the terms of this series. I'm going to be careful. The limit of the absolute value of the ratio of the n plus first term of the series divided by the previous nth term of the series as n goes to infinity would equal the limit as n goes to infinity of the absolute value of the quantity n plus 1 over n squared times x over 2. Now, the thing is, the absolute value of x over 2, well, I can write this. The absolute value of A times B is equal to the absolute value of A times the absolute value of B. And so that's what I've used to go from this step to that step. And then n plus 1 over n can be written as 1 plus 1 over n. And as n goes to infinity, that part's going to go to 1 squared. The absolute value of x over 2, that just stays as is because that's not affected by n. And and the limit will give you the absolute value of x over 2. And so by the ratio test, our series here, will converge when the absolute value of x over 2 is less than 1. See, we need to find values of x for which this power series converges, for which the sum would be finite if we put in those values of x. And that's what we're doing. Okay, let me give you a moment to copy that down. Let me know if you have any questions. Okay, so Tina, I'm going to say conditionally convergent is something that is never going to be an answer, at least in this course. I know that in the some of the multiple choices, they give you that as a choice, conditional convergence. And I've heard that is used sometimes, but I've never heard of conditional convergence in the topics that we're covering. So, well, now we need to find, now that we know, so by the ratio test, we need to find the values of x for which the absolute value of x over 2 is less than 1. Okay, so then we go to the next page. The absolute value of x over 2 is less than 1. This means then we can write that as x over 2 is less than 1 and greater than negative 1. Okay, that's how many recall doing that to remove an absolute value? If you have, like if you had, the absolute value of, let's say, d is less than 3 or less than 2, let's use 2. Wouldn't that mean then that if the absolute value of d is less than 2, then d is less than 2 and greater than negative 2, right? You'd have no trouble, understanding that the absolute value of d being less than 2, that would mean that d would have to be between negative 2 and 2. It's the same thing here. We have the absolute value of x over 2 is less than 1. That means x over 2 is less than 1 and greater than negative 1. And so x then would have, well, now if we multiply through by 2, here, okay, let me multiply through by 2 here. I got to be a little, I don't want to write sloppily, but one moment. Okay, so I'm multiplying through by a positive, so that's a positive number 2. So that's not going to change the inequality. Okay, so I go from here to here, and then that's going to give me that x is between -2 and 2. So our power series converges when x is between -2 and 2. Okay. So these are values of x where the power series converges. So if like we were to put x equals 1 in the power series, if we were to go back and put that in the power series, we would get a finite sum, because 1 is in this domain of convergence. But the question is now, could there be any more x values where our power series diverges? Okay. So let me ask you this. Let me ask you this. Here, the values of x that satisfy this inequality, which means x is between -2 and 2, that for those values of x, our power series converges. What about the values of x such that the absolute value of our ratio L is greater than 1? What about that? For these values of x, which incidentally would be x is greater than 2 or x is less than -2, okay, for those values of x, what is the series going to do? That's right, Michael, diverges. Okay, so for when x is greater than 2 or x is less than -2, for those values of x, the series diverges, because if the absolute value of the common ratio is greater than 1, the series diverges. Remember, we're using the ratio test, and we're saying that our series eventually is going to behave like a geometric series. Well, geometric series diverge when their common ratio, or the absolute value of their common ratio, is greater than 1. And geometric series converge when the absolute value of their common ratio is less than 1. So that's how the ratio test, you're exploiting that fact, because you're able to show, since the limit of the ratio of the terms of your series approaches a number, approaches a constant, the absolute value of x over 2 is a constant for some x, for any x value, you're able to say your interesting power series behaves like a geometric power series. And so you can exploit then the fact that absolute value of the common ratio, when it's greater than 1, the series diverges, and when the absolute value of the common ratio is less than 1, the series converges. And right now we have information about the power series for when x is greater than 2 and when x is less than -2, and also when x is between -2 and 2. Okay, the power series will converge when x is between -2 and 2, and the power series will diverge when x is greater than 2 or x is less than -2. Now, is that all the values of x? Do we have all the values of x accounted for on the number line? No. What's left out? What's left out is when x is -2 or x equals +2. Because for those values, the limit of our ratio will equal 1. And so the ratio test gives no information. Remember, the ratio test gives no information when the limit of your ratio equals 1. But that doesn't mean we just ignore. We can't just, ignore those endpoints. We have to manually check if our power series converges when x equals -2 or x equals +2. We have to manually check it. And by manually check it, I mean substituting in the value of x equals -2 and the value of x equals +2 and watch what the series becomes. Okay, so may I go to the next page, or who needs a little more time to copy? All right, are there any questions so far down to here? I want to make sure you're good. Okay, all right, well then let's go to the next page. Okay, so when x equals -2, what I do is I substitute in -2 for x and look at what the power series becomes. Okay, and you'll need to do this on your next exam as well. Okay, this is important work. So we get this series now where x equals -2, and we have to simplify the series. We have to simplify it. And so what I do is I say, okay, well, -1 to the nth power times -2 to the nth power is -1 times -2 to the nth power, right? But a -1 times a -2 is a 2. So the series reduces to, when x equals -2, the series becomes the sum where n equals 1 to infinity of n squared. And that series clearly diverges. It diverges. We should state why. It's obvious. The terms are getting bigger with n. But we could say then that the series diverges by the test for divergence. Test for divergence says that if your terms of your series are not approaching 0, the series definitely diverges. So this is the test for divergence that we're using here. Okay, are there any questions up to here? Okay. Well, when x equals 2, okay, then we're going to put in 2 for x, And we're going to get a nice simplification here. And again, the series, the way the series is going to behave is if I write out some terms of the series, I'm going to have -1 squared, negative times 1 squared, plus 2 squared, minus 3 squared, plus 4 squared, and so forth. So next term would be a minus, actually, right? And the terms of the series are not approaching 0. Terms of the series are not approaching 0, so it diverges. When the power series will diverge when you substitute the value x equals 2 in there. And again, we're using here test for divergence. Okay. For the series here, by the way, up here, we could write some terms too. 1 squared plus 2 squared plus 3 squared. I find it really helpful to write a few terms out. How many find that helpful, just so you have a little bit better feel? For sure. Okay, thank you, Tina. Thank you, Felicity. Well, now we've accounted for every x value possible, and we're able to write down now our interval of convergence. Okay, and so are we ready to go to the next page? Okay. All right, well then, the interval of convergence for our power series is I equals the open interval from -2 to 2. The open interval. So sometimes the interval will include endpoints. Other times it won't. And in the homework in WebAssign, you'll have like one chance to get it right. Because either the interval is on the endpoint, it's either going to be an open or a closed interval. So our interval of convergence is the open interval from -2 to 2. And then the radius of convergence is r equals 2. So what I did was I took my interval here from -2 to 2 and cut it in half. The interval is centered at 0. So half of the length of 4 is 2. The radius is 2. And we're done. We're done with that problem. Okay, are there any questions at all? Go ahead and take off my, had my email open. I mean, I'm not like looking at my email, but you know, it does go beep, beep. And so I'll turn that off because I don't mind leaving it on, but if it beeps too much, then, you know, we don't want to distract too much here. Okay, let's look at another example. Are there any questions? Look at another example. Okay, well, let's go ahead then. Here's another power series. We want to find the radius of convergence and interval of convergence. And it's important to mention that the power series is generated, you'll see how functions can generate power series. We'll go into that in a little bit, but let me let you copy the example down. Okay, so this is an interesting power series, but because, you know, we have an x minus 3 here, but the way we handle it is just like the previous power series that we did. We're going to use the ratio test to help us determine um, the interval along with boundaries, and then we have to test the boundaries. So I'm going to go right to the solution. So the nth term of the series is given here. And we look at the limit of the ratio of the n plus first term to the nth term. And we have the limit as n goes to infinity of the absolute value of the quotient of two fractions. I'll write the quotient of the two fractions as the top fraction times the reciprocal of the bottom fraction. And then I group like terms together. Okay, so let me give you a moment to copy that. Let me know if you have any questions. Okay, so, well, now what we do is we reduce the best we can each of our little expressions here. And of course, the absolute value of -1 to the first power, that just, becomes a positive 1. And we get this, the limit as n goes to infinity of the quantity 2n plus 1 over 2n plus 3 times the absolute value of x minus 3. So it's important to remember we're always using this property that, a times b equals the absolute value of a times b equals the absolute value of a times the absolute value of b. We're always using that property, okay, to get to our last part here. Now, what is 2n plus 1 over 2n plus 3? What is this coefficient approach as n goes to infinity? What will that coefficient approach there? As n gets large. That's right, Rodrigo, 1. And so we get the absolute value of x minus 3. Now, what do we do with the absolute value of x minus 3? What are we going to do with that? Remember, we're applying the ratio test. The ratio test is telling us that our power series eventually behaves like a geometric power series with a common ratio of the absolute value of x minus 3. Under what conditions is the power series going to converge based on this common ratio? What do we have to do with that common ratio absolute value? I mean, that's the L, right? That's the L in the ratio test. What do we have to do with that now in order to help us find the interval of convergence? Okay, Michael, find the boundaries, but how are we going to get to the boundaries? How are we going to like, we do need to get to the boundaries, but to get to the boundaries, I need to have an interval. Okay, so, and Michael says all right, so what Michael did was he set the absolute value of x minus 3 less than 1. Good, Michael. That's what you need to do. So by the ratio test, our power series converges, okay, when the absolute value of x minus 3 is less than 1. Okay, when this is true, and that means that an x minus 3 is less than 1 and greater than negative 1. And so in this case, x is between 2 and 4. Our series will converge when x is between 2 and 4. Now I want to make sure I'm pacing myself okay. Let me give you just a moment or two to think. Let me know if you have any questions. All right, so now the question is, are there any more x values where our power series converges? Okay, so of course, what we care about then is when the absolute value of the common ratio equals 1, because for those two x values that will solve this equation, that's when x equals 2, x equals 4, x equals 4, the ratio test gives no information. Okay. Okay, so we got to take x equals 2 and do what with it? Let's start with x equals 2. What are we going to do with x equals 2? Because I'm going to give you a little chance to work on these problems. We have to okay, plug it in the series. That's right. So that's what we do. We must manually check if our power series converges at x equals 2 or x equals 4. And so when x equals 2, we substitute 2, x equals 2 in the power series. Notice I am showing my work. Okay, this is showing work. Okay, and again, many of you do show your work well, but there are a few of you who do not show your work well. And you miss points on the exam because of that. I don't want that to happen, you know, so you can always use, you know, my examples as a good model of what kind of work you need to show, right? You always can use my examples to you know, help you. So, okay, all right. So, well, negative 1 to the nth times negative 1 to the nth, and the numerator here is negative 1 to the 2nth power. And 2n power, that is what kind of power? I'll give you a hint. Starts with an E, and we need 3 more letters here. Starts with an E, 2 to the nth power for any n, no matter what n is. 2 to the nth power is going to be what kind of power? Give you another letter. Even, the good candy. That's right. Okay. Very good. And so even power, you got -1 to the 2nth power. So you know, like you'd have, when n is 0, you'd have -1 to the 0th power. When n equals 1, you'd have -1 squared. When n is 2, you'd have -1 to the 4th. Right? It's a little sloppy there. We can make that better. I mean, what's true about -1 to any even power? What's it going to equal? -1 to any even power. It's going to be +1. Good, Cologne. That's -1 to the 4th there. So hence we get a 1 in the numerator. So what we're going to do now is we don't just, this series is going to diverge. Okay, this series here, the series n equals 0 to infinity of 1 over 2 times n plus 1 diverges. But do we just say diverges? No, we have to show it. So by the limit comparison test, we're going to let the a sub n be 1 over 2n plus 1 and b sub n be 1 over n. And then we're going to look at the ratio of the nth term to the a-nth term to the b-nth term, and we'll get out a half. And therefore, by the limit comparison test, our power series has to diverge at x equals 2 since the harmonic series diverges. Okay, when we're using the 1 over n here, that's because a harmonic series has the term 1 over n in it. And that series, so we're saying basically that our series here, our series is the sum where n goes to 0 to infinity of 1 over 2 times n plus 1. The harmonic series is the series n equals 1 to infinity of 1 over n. If we look at the ratio of the terms of these two series, as n gets large, our series here, the terms of our series here, are basically going to be 1/2 times the terms of the harmonic series. Okay, they're going to be, our series are going to behave like a harmonic series. They're just going to be half as small, which makes sense because you have the 2 times n here, and we know that the little 1 here, when n is large, that little 1 doesn't affect things. Okay, so our series here, as the terms of the series get large, I want to be careful. As we look at the series, I didn't say that right. As we look at our series here, when n is large, as we look at how the terms of the series behave, when we're, like at the billionth term or way far into the series, the terms of our series are going to behave like the terms of a harmonic series, just one half of those terms. Okay, so our terms of our series are in proportion to the terms of the harmonic series by half. But that means that if the harmonic series diverges, our series diverges. Now, similarly, may I go to the next page?
No, wait.
Okay, all right.
What does this mean?
C here this C is just in the limit comparison test. They talk about the limit of, as n goes to infinity, of an over bn equaling C, equaling constant C greater than 0. And so I'm just saying 1/2 is equal to that C. Good question, Tina. All right, are there any other good questions? Oh, no problem, no problem. Okay, so now let's try x equals -2. Or x equals 4, sorry. X equals 4 was the other value, right? We're going to put 4 into the series, as we do here. We let x equals 4 right here. And the series is going to become n equals 0 to infinity of -1 to the nth power over 2n plus 1. That converges by the alternating series test. Okay. I mean, we could write this like this. Hopefully I have enough room here. We can write the series like that. And it's clear that the 1 over 2n plus 1, okay, that part of the coefficient, that we call it d sub n, decreases with n, and it approaches 0. So our series will converge by the alternating series test, because those are the two conditions that tell us when an alternating series converges. Okay, alternating series test was back in section, well, it was just in section 8.4, right? Okay, so our power series converges at x equals 4 then. And so this now becomes our interval of convergence for the power series. It's going to be an open interval on the left. Open interval on the left, because 2 is not in the interval of convergence. And then closed interval on the right, because 4 is included in the interval of convergence. And the radius of convergence would be equal to 1, because the length of our interval is 2, half of 2 is 1. Okay, let me know if you have any questions. Let's see. Tina asked, will the radius be the same? Yes, that's correct, Tina. It doesn't matter if the endpoints are open or closed in your interval. The radius, you always take the right number subtract the left number, get the difference, and divide by 2, and that gets you your radius of convergence. How many think these are pretty cool problems? Well, it's a little long, Tina. It's a little long, but you know, you're going to see it's really wonderful stuff what you're learning here. If there are no questions, let me. That's right, Michael. It is the ultimate extension of the earlier material. That's right. That's exactly right. Because we are really interested in studying functions. Okay, and we're going to learn that power series functions can be written as power series, but a function is only equal to its power series over its interval of convergence. All right, and so, all right, let me stop the recording here.